Today we're going to be talking about optical switches. But first, what is an optical switch? Well, an optical switch is pretty much what it sounds like. It's a switch, well, in other words, it's a multi-port network bridge that actually connects multiple optic fibers to each other. And what this switch does, it actually controls the data between its inputs and its outputs. What this specific optic switch does is it actually converts the light signal into electrical data before outputting the light signal again. So on the right side of this presentation, we can actually visualize what is happening. So we have a light input, it generates an electrical data, and then we have an output, which is a light output. Now we're going to be talking about an all-optical switch. An all-optical switch is kind of like an optical switch. It routes multiple optic fibers, it controls its inputs and outputs, but what's special about this all-optical switch is that it does not do any electrical data conversion. Previously, an optical switch had a light input, generated electrical data, and had a light output. But what this all optical switch does is that it has the light input and it keeps the light input, so there's no electrical data conversion. It actually routes the entire light signal coming from the optical input to the output. What's great about this is it does not have any latency, it does not have data corruption, or it does not have timing jitter. I wanted to talk a little bit more in depth on the all optical switch. The all optical switch is actually a circuit with no packet routing. What this means is that it does not convert the IP packets that it's receiving, since it gets the IP packet from the input and it directly pushes that to the output. Also, the switching that it's using the all optical switch, it's the triple O switching. Well, this stands for optical input, optical switch core, and optical output. I previously talked about this on the other slide, but I just wanted to include that since I didn't really specify the type of switching that it was happening. Now, what types of signals can the all optical switch route? Well, pretty much any wavelength that propagates through the optical fiber, which includes the single mode signal, the multi-mode signals, and since it's running the triple O switching, it can actually route video, audio, data, and optical sensor signals with up to 400 gigabytes per second. Now, here's an important question. We already talked about optical switches and the benefits of the all optical switch. But now, why use fiber switching? Well, there's a lot of benefits in switching to fiber switching. Well, first of all, it has better benefits over conventional copper switches. Why? Because the first layer of which is the fiber layer, which is used for the optical switches, is mostly static. Well, this means that the cabling needs to only be done once and can actually be reconfigured remotely. So there's no need for patching or manual intervention. Another benefit for optical switches is that it reduces the cost, the power usage, and the electrical conversion delays. So we're getting three benefits out of there instantly. First of all, the cost is really important. also the power usage. And what's really important is having zero latency, which goes back to having no electrical conversion delays. So what's also important is that it also maintains an inventory of the cross connects routing.
Hello, now we're going to talk about modulation. The modulation is the way we can modify the signal so we can transport information. Usually, are three basic parts of the light wave we can modulate to transport that information. Is the amplitude, the phase, and the polarization. Actually, is three ways very popular to modulate the signal. That is the IMDD, DSPK, and current modulation detection. And we're going to talk more detail in the next slide. The first one is IMDD, intensity modulation and direct detection. This one is one of the most cost effective. It have the free spatial optical communication and the indoor visible light communication. This format basically is just a turn on, turn off signal. Basically, that you do is turn on the light and turn off the light inside the fiber optic. This was represented in ones and zeros. This is one of the more simple modulation compared the other ones. This one is because the receptor and the transmission are very simple, but the sensibility of the receptor is very efficiency when you try to transmit very simple data. But they are very limited when you try to do more complex communication. And basically, this is the biggest issue of this kind of modulation. For the DSPK differential phase gauging, we have a more complex method to qualify the information. In this one, actually, we have information in -1, 0, and 1. One of the most common formats to qualify this modulation are the differential binary phase shift gauging. This this basically use phase differential between the adjacent symbols carried in the information of the bits, and they use an optical delay interferometer. And this is because the signal it compared with the delay and it compared by itself to convert the phase modulation into an intensity modulation that can directly detected by the square law detection. When optical modulation is more complex than the last two modulation methods, but it can give you more advanced technology and can give you better results. First, we can see that this method it let have transmission over two polarization. This basically that it makes they let you have more bandwidth, more flexibility on the angle, and better performance. Actually, this thing it solves a lot of problems that right now have the network providers. This method that it makes it have digital signal processor from the transmitter and the receiver systems, and this digital processor that it makes solve a lot of problems that they just turn on, turn off, like the ADD and the glass method. Actually, in the current optical modulation, one of the advantages we have is like we can anticipate error correction. This basically that it makes is you have a big gain in the decision solve. This basically that it allows the signal they pass through in a very long distance, it requires less uh, quantities of point to regenerate that information. This make more margin to allow the signal bits go to longer distance. Actually, the other thing is the conformation spectral. This allow that you have more capacity in reconfigure the optical add drop multiplex that it calls ROADM, and this that it makes it make more efficient the spectral super channel to have a more fundamental and have a more connection flexibility. The one of the strongest things that it makes the current optical modulation is it easy to program. This means like it can adapt to very different technology and they can adapt to very different network and application using the same board. And this because as I talked in the last slide, this is our digital processions of the data, and basically with some change in the code, you can do very different application. And the stronger part is that have a very strong mitigation dispersion. As we see in the class, the dispersion they can make a lot of struggle on the optical data signal. This make a better performance and more bandwidth on the processor and have more current signal. This means like when you send information from through the longer distance to the longer with a big bandwidth, they don't distort that easy. Actually, with this one is when you can go from 200 gigabytes to 400 gigabytes, and is what it tried to take right now to the technology.
Coherent transmission is a system that combines amplitude modulation, phase modulation, and polarization. In this case, we can transmit greater amounts of information. Advanced coherent optical has several key attributes, which are a high gain soft decision, spectral shaping, programmability, and strong mitigation to dispersion. We also have coherent detection, which means that an optical receiver can track the phase of an optical transmitter. On figure 1, we can see how a coherent detection works in a wireless system and an optical coherent system. Many of the systems operating today have coherent receivers, but some designers are starting to think that non-coherent option could be a better option for them. In this slide, we can see a table and the advantages of coherent and non-coherent.